This list of ions cannot react with water because these ions are the conjugates of strong acids and bases. As an example, sodium. Now we know that sodium hydroxide is a strong base. It dissociates 100% in water. Because it goes 100% in water, we know that sodium cannot combine with hydroxide to form sodium hydroxide. Similarly, sodium is unable to react with water to form sodium hydroxide as well, because it is impossible for a strong acid or base to be formed while in the presence of water. Instead, strong acids and bases react 100% while in the presence of water. So sodium, although it's positively charged, might have been attracted to the negatively charged electron pair on oxygen and might have combined the sodium with the hydroxide. That cannot occur. Similarly, taking a look at chloride, which is also on the list, we know that hydrochloric acid is a strong acid. It dissociates 100% in water, leaving chloride and hydronium. Because that reaction goes 100%, chloride is unable to react with water, actually hydronium, to give hydrochloric acid. Similarly, chloride is unable to react with water to give hydrochloric acid. It is impossible to form this strong acid while in the presence of water. So this conjugate of a strong acid, chloride, cannot combine with the positively or relatively or partially positive hydrogen on water to form hydrochloric acid. Those list of ions cannot react with water. However, many other ions can. Most anions, in fact, can react somewhat with water and form hydroxide. As an example, acetate. This can combine with the relatively positive hydrogen on water, and when doing so, can form acetic acid and also leave some hydroxide. We generally say that anions create basic solutions when they're creating these hydroxides. Now, some other cations can react with water and form protons. This list of cations is a list of small, so low volume, low radius, highly charged cations. Because they're quite relatively or fully positive over a small area, the positive charge of these cations attracts the relatively negative oxygens of waters, and hence can form or can kind of attract and then bind with those OH groups, leaving protons. So as an example, we have aluminum, which has attracted 6 waters to it. Now this can strip. This can strip a proton from one of the waters towards another water, leaving a hydroxide instead of a water near that aluminum, and giving an extra proton to water, forming, please edit this, hydronium. So essentially what we saw was that aluminum, which was positively charged, reacted with a water. It then attracted the relatively negative oxygen of the OH of that water, leaving then aluminum with an OH and now only a +2 charge, and leaving then a separate proton. Although this is the actual process that occurs, this is one way to think about it. So we'll often be doing math with regard to the acidity or basicity of salts. For example, you might be asked, what is the molarity of a 0.15 molar sodium acetate solution, given that the Ka of acetic acid is 1.8 times 10 to the negative 5. Now, we want to find the pH. So we need to first consider that many of these salts that were described break up into ions immediately and 100% in water. For example, sodium acetate is well soluble. It breaks up into separate sodium and acetate ions. Now that sodium will no longer or no further react with water. That's part of the list of ions which do not react with water. But acetate can react with water. we saw that negatively charged ions, anions, often react with water and form hydroxides. This acetate is negatively charged. It attracts the relatively positively charged part of water, and then leaves a hydroxide. So this forms acetic acid and hydroxide. So then we need to consider what is the pH. Well, you can determine this by knowing the final concentration, or the equilibrium concentration of hydroxide. So build an ice table as usual. Now, this ice table, however, allows us to have the products of the reactants for some reaction in which acetate is acting as a base. Here, acetate is acting as a base. It's grabbing a proton from water. So this is governed by Kb. However, we were only given Ka in the reaction, or actually in the problem. And so we need to actually find the Kb of acetate from the Ka of acetic acid. So Kb is equal to Kw over Ka. Kb is equal to 1 times 10 to the negative 14 over 1.8 times 10 to the negative 5, or 5.55 times 10 to the negative 10. So now we can solve for x, and we find that x is equal to 9.12 times 10 to the negative 6. Now, x is equal to the concentration of hydroxides, not protons here. And so our hydroxide concentration is 9.12 times 10 to the negative 6, and from that we can find the pOH and then the pH. This makes sense here. We have a pH which is greater than 7. Being greater than 7, we have a basic solution. This is what you would expect if you had a basic salt put into water. As an example, sodium acetate, which has acetate, an anion which can react with water, and sodium, a cation which cannot react with water. That should give us a basic solution. Finally, say that you have a solution of sodium bicarbonate. You're told that the Ka of bicarbonate is 4.8 times 10 to the negative 11, and that the Kb of bicarbonate is 2.4 times 10 to the negative 8. Ka and Kb of the same compound. Will this solution be acidic or basic? Now, let's see, so that bicarbonate can act as an acid. It can release a proton into water, increasing the concentration of hydronium. This is governed by the Ka. And also it can act as a base. It can accept a proton from water, leaving hydroxide. This is governed by Kb. Which of these reactions will occur more significantly, and hence will determine whether the solution is acidic or basic? Well, this top reaction, it is governed by Ka, which is 4.8 times 10 to the minus 11. Now, the greater the K value, the greater the extent that the reaction occurs, because there's a higher concentration of product to reactant. Now, Kb, that's 2.4 times 10 to the negative 8. We see that though this top reaction goes to some extent, the bottom reaction occurs more significantly because it has a greater equilibrium constant. Kb is greater than Ka. Hence, we should expect to have a greater concentration of hydroxides than hydronium in the solution. Hence, we should have a basic solution. Thanks for watching, guys.